Have you ever run into a situation where you've got these private resources, these digital assets tucked away safely, but they need a way to reach out to the internet to talk to the outside world?
It's a common challenge. You don't want to fling the doors wide open, expose everything.
It's all about controlled access. And that's what leads us to the core of what we're diving into today. Network Address Translation, or NAT, within AWS.
How it all works within your virtual private cloud, your VPC in AWS.
Which is awesome. But what we're going to try to do today is really hone in on the smart, secure, and efficient ways to achieve this connectivity, because you're right, it can get complicated.
There are a lot of moving parts, and picking the right approach is key.
Think of it like giving your internal applications a carefully managed phone line to the outside world.
With a discerning operator handling the connections.
Exactly. Mission for this deep dive: we need to lay out the options AWS gives us for providing internet access to private subnets.
We'll look at the pros and cons, the trade-offs, the gotchas, the things you really need to think about.
Perfect. Let's kick things off by looking at what we might call the classic way of doing NAT in AWS, NAT Instances.
Ah, yes. The trusty NAT instance. Still relevant in some cases.
Now, for those who might not be familiar, what exactly is a NAT instance in the AWS world?
At its heart, a NAT instance is just an EC2 instance, a virtual server, that you launch in a public subnet within your VPC.
Why is that important?
Because the NAT instance itself needs to be able to communicate with the internet, right? It needs a route to an internet gateway, and that connection is only available in the public subnet.
It's got to be able to reach out if it's going to be forwarding traffic.
The NAT instance has a public IP address, which it uses to interact with the outside world.
Got it. Now, I remember reading something about having to disable a source-to-destination check on a NAT instance.
By default, EC2 instances are set up to only send and receive traffic where the source or destination IP matches its own.
Okay, that makes sense.
But a NAT instance, its job is to forward traffic on behalf of others.
Yeah.
That traffic is going to have a different source IP.
It's coming from the private instances behind it.
Exactly. So disabling source-to-destination check tells AWS essentially, hey, this instance is allowed to forward traffic for others.
It's giving it permission to act as a proper router.
Precisely.
So once we have this NAT instance up and running, configured correctly, how does the traffic from those private subnets actually get to it?
This is where route tables come into play. You can think of a route table as a set of directions, like a map for network traffic.
Okay, guideposts.
For your private subnets where your applications are running, you need to configure their route tables to say, hey, any traffic destined for the internet, send it to the NAT instance.
So the private subnet knows, okay, if I need to talk to the outside world, go through this.
That's how you direct the traffic.
Now, security, always a big concern. What are the key security things we need to think about when using NAT instances?
Security is paramount. You'll primarily manage security for your NAT instance using security groups.
Those are like firewalls at the instance level, right?
That's a good way to think about it. So for inbound traffic to the NAT instance, you want to be very specific. Allow HTTP and from your private subnets. That way, they can access websites.
Makes sense.
You might also want to allow SSH, but only from very specific trusted IP addresses.
Only the folks who need administrative access.
Exactly. And even something simple like ICMP, which is used for ping.
Just to check if something's reachable.
You might need to explicitly allow that in the NAT instance's security group.
Good point. It's easy to overlook the little things, but they do have drawbacks.
They're not a perfect solution.
What are some limitations we should be aware of?
Well, one of the biggest is that they're not inherently highly available. If your single NAT instance fails, the instances in your private subnet lose internet connectivity.
Not good.
To get high availability with NAT instances, you need to do some manual configuration across multiple availability zones.
Those are the different data centers AWS has.
Exactly. And it often involves things like auto-scaling groups, ASGs, for short, to handle failover.
Sounds complicated.
And then there's bandwidth. The amount of throughput your NAT instance can handle is directly tied to the instance size.
So if you have a lot of internet traffic, you might need to scale up to a larger instance.
Exactly, which means more cost. And then there's the general management overhead. You're responsible for patching the operating system, security updates, all that.
Keeping it healthy and secure.
And of course, you're paying for the per hour cost of the EC2 instance itself, plus any data transfer costs.
How would you say a NAT instance compares to a regular EC2 instance in terms of these limitations?
Well, with a regular EC2 instance, you're not setting it up specifically for routing traffic for others. So High availability is going to be specific to that instance, not for an entire subnet's internet access.
Okay, makes sense.
Bandwidth is still tied to instance size, but again, not a bottleneck for a whole subnet's outbound traffic.
Right.
Well, that's always your responsibility for any EC2 instance you manage. Cost is similar in structure you pay per hour and for data transfer. But with a NAT instance, you might have those additional data transfer costs because it's handling traffic from multiple instances.
It's acting as a gateway.
Exactly. And a NAT instance needs a public IP to function, whereas a regular private instance, you could technically use a NAT instance as a Bastion host.
We'll get to those.
We will, but it's not really its intended purpose.
Right. Tool for the right job.
Exactly. And the security group management for a NAT instance is really about controlling the flow of traffic for others.
Whereas with a regular instance, it's about securing that instance itself.
Precisely.
NAT instances work, but they require a fair bit of babysitting. They're not the most resilient or scalable option.
Well, they really embody the AWS philosophy of managed services. AWS takes care of the underlying infrastructure so you don't have to.
Sounds good to me. Less for us to worry about.
They're designed to be more scalable, highly available, and easier to manage than NAT instances.
What's involved in setting up a NAT gateway?
You create a NAT gateway within a public subnet in your VPC.
Still in a public subnet, just like a NAT instance.
Because it needs that internet connectivity. And you associate an elastic IP address with it.
Ah, elastic IPs. They're the static public IPs we allocate in AWS.
That gives the NAT gateway a consistent public IP it can use.
So we've created the NAT gateway. It's got its elastic IP. How do we route traffic to it from our private subnets?
Just like with NAT instances, you modify the route tables of your private subnets. But this time, instead of pointing the internet-bound traffic to an EC2 instance, you point it to the NAT gateway.
One of the big benefits I remember is reduced management overhead.
Absolutely. With NAT gateways, AWS handles the patching, the maintenance.
We don't have to worry about keeping the underlying operating system up to date.
And unlike NAT instances, you don't manage security groups for the NAT gateway itself. AWS takes care of that.
Less for us to worry about, more time to focus on our applications.
Precisely.
What about scalability and availability? I seem to recall NAT gateways being a big improvement in those areas.
NAT gateways are designed to scale their bandwidth capacity automatically, up to 100 GBps per gateway, as needed.
Wow, that's a lot of bandwidth.
It is. They're built with redundancy within an availability zone.
So if one of the physical servers hosting the NAT gateway fails, AWS automatically routes traffic to another one.
Exactly. You get automatic failover within that AZ.
What if the entire AZ goes down? Are we still vulnerable?
That's a great point. For true fault tolerance, you'd want multiple NAT gateways, each in a different availability zone.
Okay, spread the risk.
And then you'd configure your route tables so traffic from instances in a specific AZ goes to the NAT gateway in that AZ.
Keeps things nice and isolated.
Exactly. No need to create complex routing between the AZs for NAT gateway redundancy.
So if one AZ goes down, the others can keep chugging along.
Precise.
Okay, what about cost? How does pricing for NAT gateways work?
It's based on two things: an hourly charge for the NAT gateway being active and a charge for the amount of data that goes through it.
Similar to a NAT instance.
It is, but you have to factor in the operational cost savings of not managing the NAT instance yourself.
Less time spent on maintenance.
Potentially a higher per hour cost, but less management and better scalability and availability.
Makes sense. One last question on NAT gateways. Can we use them for administrative access, like a Bastion host?
No, NAT gateways are designed for outbound internet access from private subnets. They're not for inbound connections.
So for secure admin access, we need to look at something else.
We do. That's where Bastion hosts come in.
Ah, yes. The Bastion host. How do we securely get in for management?
That's the Bastion host's job. They're sometimes called jump servers. They provide a secure way to access EC2 instances in private subnets.
For things like SSH, right?
It's basically a hardened EC2 instance sitting in a public subnet that acts as a secure entry point.
Okay, so the Bastion host is publicly accessible.
It has a public IP address, but access to it is very tightly controlled.
How so?
To connect to an instance in a private subnet, you first have to SSH into the Bastion host.
Okay, it's like a two-step process.
Right. Once you're logged into the Bastion host, you can SSH into the private instance using its private IP address.
What are the key security group rules we need to configure for Bastion hosts and the private instances they're protecting?
For the Bastion host itself, you want to be very strict. Allow SSH traffic, but only from very specific public IP addresses or ranges.
Like your corporate network or your own home IP if you're working remotely.
Minimize that attack surface as much as possible.
Makes sense.
And for the private instances, their security groups should only allow SSH traffic from the Bastion Hosts IP or security group.
So they can only be accessed through that secure intermediary.
Precisely.
What does it look like to SSH through a Bastion host? Is it more complicated than a direct connection?
It's a couple of extra steps. First, you SSH into the Bastion host using its public IP. You'll need the Bastion host's private key for that.
That's the standard SSH process.
Once you're on the Bastion host, you SSH to the private instance using its private IP. And you'll need the private instance's key for that.
Okay, so a little bit of key juggling.
You might need to download the private key to the Bastion host, set the right permissions on it, and then use it for the SSH connection.
A little fiddly, but doable.
Definitely doable.
If we're accessing a private instance through a Bastion host, does that instance have general internet access?
No, it doesn't. The Bastion host is just a secure tunnel for management.
The private instance is still isolated, unless it has a NAT gateway or instance.
Exactly. You can SSH into it, manage it, but it can't just start reaching out to the internet.
Could we theoretically use a NAT instance as a Bastion host?
Yes. You could open up SSH access to it.
Oh.
It's not recommended.
Why not?
NAT instances are designed for network address translation. Adding Bastion host duties complicates the security setup.
Potential for things to go wrong.
And it could create a single point of failure for internet access and administrative access.
Not ideal.
It's better to keep those functions separate. Dedicated Bastion hosts for secure management and NAT gateways or instances for outbound internet.
All right, separation of concerns, good practice. We've covered getting in, getting out to the general internet. But what about when our private instances need to talk to other AWS services?
Internal conversation.
And that's where VPC endpoints come in.
VPC endpoints are all about providing private connectivity to AWS services within your VPC.
So instead of going out to the internet and back in, we can have a direct private connection within the AWS network itself.
That's the idea. It enhances security, can improve performance, and keeps things contained.
Now, there are two types of VPC endpoints, right?
There are interface endpoints and gateway endpoints.
I could break those down for us.
Interface endpoints, they're powered by this thing called AWS Private Link.
Okay.
When you create an interface endpoint, it gets its own elastic network interface, or ENI, with a private IP address in your VPC.
So it's like its own network interface within our VPC.
Exactly. ENI acts as an entry point to the AWS service.
The traffic goes through that.
Use security groups to control access.
So we can be specific about who can talk to them.
Exactly. They support a wide range of AWS services.
Like I said, versatile.
But they have an hourly cost and a cost per GB of data processed.
What about gateway endpoints?
Gateway endpoints are a little different. They're specifically for accessing S3 and DynamoDB.
Those are two big ones.
They create a gateway as a target in your VPC route table.
So no IP addresses or security groups to manage at the endpoint level?
That's right. And they scale automatically with your traffic.
Wow, they sound pretty attractive for S3 and DynamoDB.
Can you give me a quick scenario where we might use a gateway endpoint to access S3 from a private subnet?
Imagine you have an EC2 instance in a private subnet. It needs to access an S3 bucket.
Common use case.
Now, if you wanted to do this over the public internet, you'd need a NAT gateway or route to the internet, all that. Right, we've covered that.
But with a gateway endpoint, you create the endpoint associated with the route table of your private subnet.
So that traffic destined for S3 goes through the endpoint.
Exactly. And then even if you remove the route to the internet,
the instance can still talk to S3.
Because the traffic is flowing privately through the VPC endpoint.
Like a secret tunnel to S3.
That's a great way to put it.
So for S3 and DynamoDB, gateway endpoints are usually the way to go.
Unless you have specific needs, like accessing those services from on-premises over a VPN or needing cross-VPC access.
Those are the edge cases we mentioned earlier.
Exactly.
All right, we've covered a lot of ground today. NAT instances, NAT gateways, Bastion hosts, VPC endpoints.
We've explored the connecting private subnets in AWS.
And the key takeaway is that the right approach really depends on your specific needs and requirements.
You have to weigh the security, the management overhead, the cost, the scalability, the availability.
Absolutely. So for you, our listener, as you think about your own AWS environment, your security posture, your use cases, which of these methods or combination of methods do you think is the most compelling for what you're trying to achieve? And what are those key trade-offs you'll need to evaluate?
Maybe revisit the source materials with this fresh perspective, or explore the AWS documentation.
Thanks for joining us for this deep dive.
It's been a pleasure.